this video, we are going to be defining what an angle is, talking about how we name and discuss and diagram angles, and then we're going to look at something called the angle addition postulate, and hopefully we can get all that into one quick video. So let's start off by defining what an angle is. Okay, so an angle is formed by two rays that have the same endpoint. Okay, so we are going to measure in an angle the space in between those two rays. Okay, and that's going to be when we measure angles, what we're actually measuring. How far apart are the two rays? So here's just a couple other quick pieces of vocabulary. Okay, the actual rays in an angle we call the sides of the angle. We don't necessarily refer to them as rays, but they are rays. Okay, and that endpoint that they share is called the vertex of the angle. So if I come over to my diagram really quickly here, just to kind of see what we're talking about, I would say from A, kind of traveling in this direction, that's a ray, right? So remember, rays end on one side but continue forever on the other one. Okay, so I have a ray AB, okay, and then I have another ray that starts at A and travels towards C, okay, and I would say that's a different ray. And so the angle is the space that's in between those two rays. So that would be kind of like this little space in here where the 1 is. Okay, we would call that the angle. It's the space in between the rays. Okay, the vertex, when we refer to the word vertex, it's in this case that would be A. Okay, it's the endpoint that the two rays share to create the angle. So the vertex is going to be really important, especially when we're naming them. The vertex has to be in a specific spot. Okay, so when we name angles, there are several ways that we can name them, and I would say it depends on the situation. So we can use this little symbol, okay, by the way, is how we talk about angles. So it's kind of a bent L shape. Instead of the L going straight up, it kind of bends in. It looks like an angle, right? So we're going to use that little symbol to refer to angle instead of writing the word angle out. So this means angle, okay? So when I look at this, how do I name it? If I say this symbol, I would say this is referring to angle A. So I can use the vertex as the name of the angle. However, I can only use that when that angle is the only one at that vertex. So let me show you what I mean. If I were to do something like this, okay, and I put a little A here, I could not call this little space here A, because there are other angles that are also coming out of A. Because if I said A, maybe you mean this one. That also has a vertex of A. Maybe I mean this big one right here that goes all the way from this ray to this ray. So if we're not sure what you mean when you say angle A, if there's like, in our case here, I see like probably 8 different possibilities or more for angle A, you can't use the single letter name. Okay, so I would say in general, we're not going to use this all that much in diagrams that are any more complicated than this one that you see right here. So just be careful when you're naming it using a single letter that it's the only angle at that vertex. Okay, the more common way is this second one. Okay, and so in this second one we use a point on each ray and the vertex, and I have that kind of hiding down here. This was just to remind myself and as well as you, when you name using 3 points, the vertex should always be the middle point. Okay, so if I were to look at this and come over to my diagram, I picked a point on the one ray and a point on the other ray and the vertex, and when we name this, I'm going to call it either from B to A to C and call this angle BAC. Or I could start at the other one and call it CAB, and they are both good ways of naming it. I could not call this BCA, because that would be an angle that starts at B, has a vertex at C, and then goes to A. It would be like an angle that looks like that, and that's not what I'm trying to name. So make sure that when you name using 3 letters, that the vertex angle is the one that's in the middle of those 3 letters, but the other 2 can be wherever you want. The third possibility is maybe I didn't use any points at all, and I just gave you an angle that looked like this. And in cases like that, they'll typically put a number in the space. So if I tried to use either of these other ones, I can't, because I don't have the vertex named at all, and I don't have any points on the rays to name them as well. Let me put little arrows on here so they're actually rays. Okay. So in this case, they may put a number in the angle space itself, and you could also call it angle 1. So there are different ways, and again, it's more just depending on the situation how we name them. Okay, so keep that in mind as we go through. You'll see angles named in different ways. Okay, so here's your quick definition of what how we measure angles. So we have something called the protractor postulate, and if you remember from probably 2 videos ago, we had something called the ruler postulate. And this is the same thing as the ruler postulate, but it's for measuring angles instead of measuring segments. It's basically saying that all of the space in between the 2 rays can be assigned to a number, and in order to assign a number, we have to use a circular measuring tool, which we call a protractor. So instead of us using a straight line measuring tool, which is a ruler, we're using a circular or semicircular measuring tool, and we're putting numbers all around the outside so we can assign all the space in between A and B, between ray OA and ray OB with a number. Right? And so we will measure the distance from OA to OB by subtracting the number, the coordinate that we assign here, which if you can see in my diagram right here, it looks like I have 55, okay, and then the one over here, it looks like I have, I'm sorry, not 55, that would be one, we just have to be consistent, so I'm going to, okay, so we'll use this one, so 55, and over here I have 180, right, if I'm using the outside numbers, okay, the outside number for OA is 55, and when I come over to OB, it looks like it's 180. So if I were to figure out how long or how many degrees are there, which is the units we use to measure angles, I would say it would be the absolute value of 55 minus 180. Well, 55 minus 180, let me make sure I don't get my math wrong. Okay, that looks like 117 minus 5 is 125. Okay, so 125, the absolute value of negative 125 is 125 degrees. Okay, so that's kind of like the generic, how do we measure them? Well, we pull out a protractor, we put it up against the angle, and we look at the numbers, and we subtract the numbers, and that's how we get the measurement. So very similar to the ruler postulate, but we're doing the protractor measuring tool instead of the ruler measuring tool. Okay, so here are some key types of angles, things that you've probably seen in the past, with the exception of the last one. Okay, so we call certain types of angles, we can classify angles as either acute, right, obtuse, or straight. Okay, and every angle will fit into one of these 4 categories. So if the angle is between 0 and 90 degrees, but not 0 degrees and not 90 degrees, okay, so between 0 and 90, we call it an acute angle. So let's say smaller than 90 degrees. Okay, if it's equal to exactly 90 degrees, we call it a right angle. Okay, if it's between 90 and 180, but not equal to 90 or not equal to 180, somewhere between those values, we call it obtuse. So again, we'll think about that as larger than 90 degrees. Okay, and then if it's exactly equal to 180, we're going to call it a straight angle, and that's because if you notice, I got basically a straight line. When I pull it out all the way to 180 degrees, I end up with just a straight line, and so we call that a straight angle. Okay, so keep those in mind. We're going to be referring to those as we talk about angles. Okay, so let's take a look at a couple of quick ruler postulate problems, and as we do these measurements, we're also going to classify them as either acute, right, obtuse, or straight. Okay, so let's look at measure of angle LKN. So again, let's look at the naming. This says start at L, go along the ray until you get to the vertex of K. So let me grab my line tool, it'll be a little bit nicer. Okay, so I'm going to say, oh, actually maybe I can just use my highlight. We'll highlight. That'll look a little nicer. Okay. So my highlighting, I'm going to start at L, and I'm going to travel down towards K, hit K, okay, and then travel towards N. Well, N is over here, so I'm going to go from K over to N. Okay, so they really want to know what is the measurement of the space in between these 2 highlighted lines. So I'm going to get the numbers off of my protractor, and again, I'm going to use the outside edge. You could also use the inside edge, and that's fine as well, but I feel like using the outside edge. So I'm going to say the measure of angle LKN, okay, is, it looks like 35, the absolute value of 35 minus 180. Okay. I think that's the one we just did. Okay, so this would be the 100. So let me again just double check. I don't want to get my math wrong. Okay, so this would be 17. So 145. Okay, so I'd say 145. Okay, I can't do those borrowing problems in my head either. Okay, so we'd say that the measure of angle LKN is 145 degrees, and then I'm going to classify that, and we're going to say because it is bigger than 90 degrees. Okay, but not equal to 90 or 180. It's just kind of in the space between 90 and 180 that I'm going to call this an obtuse angle. Okay. So I'm going to do one more really quickly, and that's really all we're going to do with these. I think you get the idea. Okay, so let's do the next one. It just says JKL. So let me grab my highlight tool so we can see what JKL looks like. Okay, so start at J. Okay, we're going to move down to K, which is the vertex, and then we're going to move over to L, which is up here. Okay, so JKL is the space in between those two highlighted rays. Okay, it's this space right here. And so again, I'm going to say that the angle JKL is the absolute value of where JK is at 90, okay, minus, we use the outside edge, and we're saying this one's at 35. Okay, so 90 minus 35 is 55. Okay, so I'll say 55 degrees. And 55 degrees is between 0 and 90, so we would call that an acute angle. Right? So I think you get the idea. Okay, I'm not going to just keep doing these forever, but this is what we're really trying to get at, is that if you want to measure angles, put a protractor up to it, you can measure the angles by subtracting the values that we assign on the protractor. Okay, so let's talk about a couple more definitions, and so we can get to the angle addition postulate. So just like congruent line segments are lines that have the same length, we're going to say congruent angles are angles that have the same measure. They are the same number of degrees. Okay, so I'm not going to spend a lot of time on this. Here's the one thing I'll point out, just again, notation-wise. When we're talking about the actual angles themselves, we say angle A and angle B, which I can use those names because this is the only angle A, this little red one here. Okay, and I can use the congruent symbol. When I'm talking about the number of degrees, I have the equal sign in between them. So if this is like 20 degrees and this is also 20 degrees, I'd say the measure of angle A, which is 20 degrees, is equal to the measure of angle B, which is also 20 degrees. So this little m here is what we will put in front of the angle to specify that it's the measure of the angle, not the angle itself. Okay, so just like how when I put like AB without a line over top of it, I mean the length of AB, but if I do that, now I actually mean the line itself. Same thing here, right? When I put the little m in front of angle A, that means that I actually care about the number value. What is angle A worth? Okay, so little notation stuff, but this means the number. When I put the m in front of it, this means the actual angle itself, which is why there's a congruent symbol. Okay, here's the last little thing. If I want to say that two angles are congruent, or I want to specify to you that the measures of them are equal, that they have the same number of degrees, okay, we use this little arc, okay, in between the rays. So if I put this little red arc here, and I put also a red arc here, or any color arc, that means that it's the same. If I want to specify that the angles are different, I can use a different number of arcs. So if I go like this, okay, and I look at angle A and I look at angle B, and angle A has 2 arcs, but angle B only has 1 arc, I'm actually indicating to you that they are different measures, that they are not the same. But every angle that has 2 arcs are equal. Every measure that has 1 arc, those ones are equal as well. And I can do any number of arcs. Typically we won't get over 3, but we might occasionally see 4 arcs. So everything with 4 arcs is the same. So it's kind of like the dash equivalent from when we were doing lines. Okay, so that's just notation that you're going to see. Now let's get on to what we really came here to do, and that is to talk about the angle addition postulate. So the angle addition postulate is the same thing as the segment addition postulate, but now we're talking about angles. When we did segment addition postulate, we said if we have a big segment and we cut that segment into parts, and we should be able to add up all of the parts and get the whole segment back. This is doing the same thing, but now we're going to cut an angle with a different ray. So if I start off, okay, and again I'm just going to kind of show you a quick example. If I start off with something like this, okay, I have this big angle here, and then I decide, you know what, I feel like throwing another ray in here. I just took the big angle and I split it up into 2 smaller angles, and so I'm claiming that if you add together this little segment here, okay, and the one right here, that you should get the same measure, the same number of degrees as the big one that we started with. Okay, so just something to keep in mind. Okay, make that go away. So let's take a look at this picture over here. So what it says here is they're giving me angles that expressions that represent RQS and SQT, these 2 little spaces here. And then again over here, they're telling me that RQT, the big angle that goes from RQ to QT, that one's 155 degrees. Okay, so we're going to do the same kind of thing, and I'm going to say that the measure of angle RQS, okay, which if you're unsure about what RQS is, that's this one. Okay, that this angle, RQS, okay, plus the measure of SQT, of angle SQT, okay, which again, if you're unsure, because we just learned how to do this, SQT starts at S, goes down to Q, and then over to T, that angle should be equal to the big one, which is the measure of angle RQT. And again, just notation as I'm highlighting the big one. If you notice, these are numbers, right? RQT is a number. I have an equal sign in between my expression, which represents that numbers are involved, and I'm using this little M notation in front of each of my angles, which represents that I'm asking about the number of degrees. I'm asking about a value, not just referring to the angle itself. Okay, so here's your RQT. RQT is this big one that goes from R to Q and then from Q to T. Okay, so it's the big space that has both of the smaller ones inside of it. Okay, so now if I plug in values, it's kind of very similar again. So RQS is 4x minus 20. Okay, SQT is 3x plus 14. Okay, and RQT, they told us not in the diagram, but up in the problem itself, is 155. Okay, so I'm going to say 4x minus 20 plus 3x plus 14. When I combine like terms, I get 7x minus 6 is equal to 155. I'm going to add the 6 over, find out that 7x is equal to 161. Okay, and when I divide this by 7, it looks like I get 23. Okay, and I'm not going to do the last step of plugging back in to find out what RQS and TQS are. You can plug into those. The one thing I will point out is that in my problem I called it SQT, and in their problem they called it TQS, but remember they are referring to this same right-hand angle, even though they're named differently. Okay, so here's where we're going to end. Okay, one more problem. Okay, and that's this one. And I'm not going to actually do this entire problem, but I want to point out something. They're giving me the segments, right? So if I'm looking at my diagram down here, okay, I am seeing a diagram that represents information about DEC and then information about CEF. But when I look up at my picture, the big one, here's my big angle, right? The one that starts at DE and goes all the way around to DF. They didn't give me a specific number that represents DEF. But what they did do was they told me that DEF is a straight angle. Okay, let me grab my big one. Straight angle. Okay, and that represents that the angle is 180 degrees. Okay, so that definition of what a straight angle is, that there's 180 degrees above a straight line, is going to be really important. You might see that show up in a problem as well. So I'm not going to do this one because it's very similar to the last one algebra-wise. You can just say that DEC plus CEF is equal to 180 degrees and solve using the algebra.